In the same way that multiplication of real numbers has properties, um, the idea being that if you multiply two numbers together, you're always going to get the same kind of result. In other words, if you multiply two numbers together, you're always going to get a real number. You can multiply them in any order. You can take three numbers and multiply the first two or the second and third together first, and then multiply them by the last number, the third number, and you're still going to get the same result. Those are all properties of multiplication of real numbers. Now we're going to talk about properties of the dot product. We're talking about properties of multiplication, a particular kind of multiplication of vectors. There are three main properties that we need to concern ourselves. One is that the dot product is commutative. So if I take a vector u and I dot it with a vector v, or if I take a vector v and I dot it with a vector u, assuming u is always u and v is always v, that they're the same, that this v is the same as this v, and this u is the same as this u, then those two products will be equal. It doesn't matter which order I multiply them in. This is called the commutative property, which is the same name we give it in multiplication of real numbers. The second one is a distributive property. If I take a vector u and I dot it with a sum of two vectors, say v and w, well, the order of operations here suggests that I should do this addition first. That's going to give me a vector, right? Two vectors added together give me a new vector. When I dot this vector with this new vector, I'm going to get a scalar, which is what the dot product produces. I can do that, or I can take u and dot it with v, and u and dot it with w, and then add the two together, and I'll get the same result. That's the distributive property. The third one is the associative property of scalar multiplication over the dot product. So for example, if I take a number c and I multiply that c across a dot product, this is a dot product, so it's going to be a scalar. If I take this number c and I multiply it by this number, I'll get the same thing as if I had chosen to multiply c first by the vector u and dot that vector with the vector v, or I can take that number c and multiply it by the vector v and dot u with that vector, right? If u is a vector and I scale u, I still have a vector. This vector dotted with v is the same as this vector dotted with u. I could also write this last one as c dotted with v, sorry, c, let me rewrite that. C times v, scale v by c, and then dot that with u, because the dot product of two vectors is commutative. I can either scale v and then dot u with that new vector, or I can scale v and dot that new vector with u. C times v and c times v are both going to produce the same vector. U times, if I call that vector w, for example. W is the vector I get when I scale v by c. Well, that's the same thing that's going on here. I'm scaling v by a factor of c, so I get w. And I can dot u with w, or I can dot w with u. And because of the commutative property of the dot product, I'll get the same result. These properties are important to know about from the perspective that if you'll remember correctly, if we have two matrices, let's call them A and B, when we multiply matrix A and B, the order that we do this in does matter, right? If we multiply AB with A on the left, versus multiplying BA with B on the left and A on the right, you do not get the same thing. So the multiplication of matrices is not commutative. So it's just as important to know when a property of an operation does hold as when it doesn't. So when I dot two vectors together, I know that I can do it in either order. Let's take a look at a couple of examples. Let's let U equal 1, 2, -3, and V equal -2, 0, 1. U dotted with V is going to be 1, 2, 3, dotted with -2, 0, 1. On the other hand, V dotted with U will be -2, 0, 1, dotted with 1, 2, -3. I left a negative off back here. I'll fix that real quick. All right, so I'm going to multiply the first two components, the second two components, the third two components, and then add those together. So for U dot V, I get 1 times -2 plus 2 times 0 plus -3 times 1. That's -5. For V dotted with U, I get -2 times 1 plus 0 times 3 plus 1 times -3. I get the same thing regardless of the order that I do it in. Let's let W be the vector, let's see, 1, -1, 3. So now what I did in this step here was to verify just for a specific case that this property holds. I'm not proving this, I'm just looking at one case to sort of help convince you that this actually works. Now I'm going to take a look at the second property, the distributive property. So I have a vector U, a vector V, and a vector W, and I'm going to do this left-hand side first. Then I'll do the right-hand side, and I'll show that that equals the same thing as I get when I do it this way. So U dotted with V plus W, I need to take V, let's see, U dotted with V plus W. In this case, that's going to be 1, 2, -3, dotted with the vector that I get when I add together V and W. And addition, remember, is just component-wise. I'm going to have -2 plus 1, which is, actually, I don't think I need this funny parenthesis here. This right here, the vector I'm about to write will be the result of adding V plus W. And I get that by adding -2 plus 1, which is -1, 0 plus -1, which is -1, and 1 plus 3, which is 4. Now I'll dot those. 1 times -1 plus 2 times -1 plus -3 times 4. So here I get -13. 14, no, -15. -15. On the other hand, if I do U, so now what I'm looking at is the right-hand side here, U dotted with V and U dotted with W, and then I'll add the results together. U dotted with V, U dotted with W. U dotted with V is going to be 1 times -2 plus 2 times 0 plus -3 times 1. That will give me -5. U dotted with W would be 1 times 1 plus 2 times -1 plus -3 times 3. That's -9. That gives me -10. When I add those results together, I get negative 15, which is the same thing as I had over here. So that second property seems to hold. All right, I've run out of room again, so I'm going to try zooming a little bit here, give myself a bit more space, and then I'll do this third one down here at the bottom. I want to show you, I want to indicate or verify, at least for one case, that if I take the dot product and multiply that by a constant, or multiply a constant by that dot product, I'll get the same thing if I multiply one of the vectors by a constant, that same constant, multiply one of the vectors by that constant first and then dot it with the other vector, or multiply the other vector by that constant and dot the first vector with that result. So I've got a u and a v already here. I'm using this u and this v for all of my examples. I'm going to add to this, let's c equal, oh, I don't know, something relatively easy. I'm just trying to make a point here. Let's go with 2. So if I take c times u dotted with v for this specific c and this specific u and v, actually I already know what u dotted with v is. I did that here. U dotted with v is negative 5. So I'm going to cheat a little bit. There's no point in doing it twice. That gives me negative 10. If I take c and multiply it by u, c and multiply it by v, I'm going to get these. C is 2, so actually let me just add one more step in here. 2 times the vector u is 1, 2, negative 3, and CV is going to be 2 times the vector v. The vector v is negative 2, 0, 1. So I'm going to get, for c times u, I'm going to get 2. I get ahead of myself sometimes. 2, 4, negative 6. And c times v is negative 4, 0, 2. But now what I want to do is dot this one here, dot this with the vector v. And this one I'm going to dot with the vector u. That means when dot v, which is negative 2, 0, 1, and I've run out of room again. I do seem to do that. Let's dot u. I'll put u out front. I've got 1, 2, negative 3 dotted with negative 4, 0, 2. This is going to give me 2 times negative 2 plus 4 times 0 plus negative 6 times 1, which is negative 10. And this one here is going to give me 1 times negative 4, which is negative 4, plus 2 times 0, I won't even write that one down, plus negative 3 times 6, which is also negative 10. So this property holds. So those are the 3 primary properties of the dot product that we need to concern ourselves with.